So, okay, let's get started. So new homework is out, homework 5. I'm going to honor my word that the lowest graded, the homework in which you do the worst will not be considered towards your grade. However, I do not want this policy to be exploited. Last year, it was exploited by at least a few students who simply don't submit your homework. That's not the intention here. So if by my own random ethical standards, I feel that the policy has been exploited, I promise there will be a homework 6. And then you will have to do it. So please work on this homework. It's in everyone's best interest. It's not too hard. And it will give you some insight. Please work on it. There will also be a midterm. The midterm will be a bit non-traditional. What does that mean? I'm not going to tell you. You wait for it. It'll be fun. Midterm you will enjoy the midterm. Okay, midterm will be between type 1 and type 2. It won't be worse than type 2.
It's a take-home.
My final will be in class. The midterm will be released Thursday morning. It will be due Tuesday morning. It will be short and it will be fun. Okay, any questions about what we did last time? Okay, so let's get started. So we are going to talk about G of R, and I will show you how you can get thermodynamic properties out of G of R. So I will going to derive a relation which will be interesting, but more importantly, what I really want to talk about in today's class and in Thursday's class is something known as statistical mechanical perturbation theory. So in quantum mechanics, you have done perturbation theory, right? You have time-dependent perturbation theory, time-independent perturbation theory. In statistical mechanics, you have probably not heard of perturbation theory, but you can see why it might be useful, right? Because we have all this machinery for non-interacting systems. So if the interaction is weak, we could consider it as some sort of perturbation over non-interaction, right? And derive relations. If the interaction is strong, maybe you could come up with a ladder of weak interactions, right? You could imagine that your strings your harmonic spring is becoming, it's 0, but it's becoming stronger and stronger and stronger, and you could develop theory for this. And I like it a lot. It's also one of those things which is practically used heavily in drug design. There is a method known as free energy perturbation, which is like, I mean, it's a $1 billion method. Any pharma company uses it. It's a multi-billion-dollar method, and it's basically out of this static perturbation theory. And I also like it a lot because the guy who came up with it, Robert Zwanzig, was a professor here for many, many years. The seminar room where you do your biophysics seminars used to be his office, a really, really big office. And then the story is that they hired Michael Fisher over here, and then Zwanzig did not like it somehow, so Zwanzig left to NIH. And then I will show you in Thursday's class as to how you can derive van der Waals equation of state as thinking about it as a perturbation over hard spheres. And how does that all work? And after this, we have only one topic, which is we will look at Ising models and phase transitions. And so the last class will be whatever I wrote on this Slack channel. As I remember what I wrote? No, so Tuesday will be the last class. On that Thursday, there won't be a class. I will, however, be coming here to teach, not to an empty classroom. I will be teaching some advanced topic, probably renormalization group theory, just a basic intro. It will not be on the exam. If anyone wants to come, you can come and join. If no one comes, I probably won't teach. But if even one person shows up, then I will teach it, and we will get to that later. Okay, so let's get started. So we want to think about thermodynamics properties from G of R. For those who came late, the most important thing I said so far is do your homework 5, or I will give a homework 6. I know I sound mean. So thermodynamic properties of G of R. So what do I mean by this? So this is what I want to think about. So let's say I have a complicated n-body interaction. Okay, so R sub superscript n here denotes that we have a potential function that depends on the vector of R1, R2, R3, ... right? And it's a complicated interaction. And now this could be made up of all the things interacting with each other at the same time. We are going to restrict. So this could be made up of 2 body, plus 3 body, plus 4 body, you could have even n-body interactions, but everything is really talking to everything. That's quantum mechanics, right? Everything talks to everything at the same time. But we are going to stop at two-body interactions in what we are going to do next. Okay, we will consider that this U of R1, R2, Rn can actually be written as going to every particle I is equal to 1 to n, going to every other particle j is equal to 1 to n, and then assuming that this can be expressed as a small u. So that one is a capital U, and this one over here is a small u, that depends only on the distance between particle I and particle j. So this is known that, so here what we have done is that we have assumed that our complicated interaction is actually a sum of two-body interactions. So now I write this sum in the following manner. There is an issue here. I need to, I'm overcounting, right? I is going from 1 to n, j is going from 1 to n. So does anyone see the problem here? They can, well, more than that, I'm counting the interaction between particle 3 and particle 4 two different times, right? So this is overcounted. It needs to be corrected. And the way to correct it is to restrict this sum to do it something like I is equal to 1 to n, and then have j go from I, more than I, till n. Make sense? And then this is small u, Ri minus Rj. Yeah.
So just to clarify, you're breaking down this entire I and j are just two particles.
Any two particles, that's the summation.
And small u is
the interaction between them. So small u is a pair potential. The small u of R is a pair potential. It could be a Lennard-Jones potential, for example. A typical pair potential, most popular one is something that looks like A by R to the power 12 minus B by R to the power 6. This is just an example. You could have any complicated pair potential. And this one, when you plot it, it looks like something like this. This is some pair potential, okay? So what I want to show next is that for this, so we have a complicated n-body potential. We have expressed it as a form of pair potentials. Chandler gives a star problem where you can do it for triplet potentials also. You don't have a question, Margot, right? Yeah. Okay, just checking. No, it's okay. So my question for you is, for such n particle systems where everything is talking to everything else, but only pair at a time. And this one could be talking to this particle over here also. This one could be talking to this particle over here also. We are not saying that these interactions die down quickly, right? They could be very, very long range. So my question for you is, for such n particles, I want to calculate the average energy in we will use canonical ensemble, right? We have specified the number of particles over there, right? So there is no point in using grand canonical. So I want to calculate the average energy for such interacting n particles. How should I proceed? Any ideas? What will be the average energy coming from? Kinetic and potential energy, right? Even simpler before we get to partition function. So this is going to be kinetic energy plus potential energy. Kinetic energy we can write down using equipartition, right? Kinetic energy is simply going to be 3 by 2 NKBT. It's the potential energy that is a beast. That's really hard to calculate. If it was an ideal gas, if particles were not talking to each other, what would this potential energy be for ideal gas? 0, everyone agrees? But now we know it's not going to be 0, right? So how do we calculate it? That is the problem. So the result that I'm going to show you is, I will write down the result, okay? And then we will work through it. And I want you to take a moment when I write the result to see actually why it makes intuitive sense. So we will prove that E is equal to 3 by 2 NKBT and plus the average potential energy. Average potential energy basically means the average of my capital U, right? That I wrote in the first page. This is going to be for a pair potential. We will prove for a pair interaction system. So we have interactions, but they are only pair interactions. For a pair interaction system, that this is half integral dr1 dr2 small u of r1 r2 multiplied by rho 2 of r1 comma r2. That's what we are going to prove. Now, where did my equation? Did I have an equation 1? Yeah, this is equation 1, and this is equation 2. Does this equation make intuitive sense? I mean, kinetic energy, we know it's just equipartition. Does the term for potential energy, is there anyone to whom it looks like, oh yeah, that makes sense? For this, you have to go back in your brain cells and remember what was rho 2. Rho 2 was the probability density of finding any two particles at R1 and R2. So this is the energy if you had two particles separated by R1 and R2. And this is the probability of finding those two particles separated by R1 and R2. And this accounts for the double counting. If you did not have half, you will cover everything. So if you think about it, it really actually makes a lot of intuitive sense, at least to me. I would have written down this expression, right? Go ahead.
What about the 1/2?
That's double counting.
But going from sums to integrals.
Yes, but you are saying any particle at R1 and any particle at R2, right? So that
Oh, so you don't want twice.
I don't want twice. I just divide by half. I'm going to derive it in full mathematical theory, but hopefully it makes intuitive sense to you. And it could not have been P because we are talking about any two particles, right? So here we have made a subtle assumption. What assumption we have made? We have assumed that this small u of R1 comma R2 is same for all particles. This might not be true, right? We are assuming that particles are basically the same. We could have had an iron and carbon mixture. We could have had carbon and nitrogen and oxygen. Then you would have to worry about separate U's, right? But you could still write down this equation in a similar manner. So we need to prove this. And this we are going to use later. So let's work through the derivation, which is, yeah, go ahead, Omar.
We assume that rho of R1 comma R1 is 0. Because otherwise the Q of 0 would probably blow up.
Yeah, I think we have to, because U diverges. Now think about it. What is the probability? It's so that is kind of trivial, right? Because rho 2 comes from P2, and P2 was 0 for R1 equal to R2. You cannot have two particles. But it's kind of circular argument. P2 is 0 because U diverges, right? So P comes from U. Think about it. So it's where did we get P? We got P from U. So U takes care of that. It's kind of funny. So let's work with the proof. I'm going to go to the next page and try to not write like an elephant. So the proof, what do we need? We need to calculate the average value of capital U of Rn, right? And what is capital U? Use equation 1. So this is average value of small u modulus of Ri minus Rj, where I more than j equal to 1, and capital N. You could have written j more than I equal to 1, doesn't matter. It's the same thing, right? It's symmetric. So this is the average we need to calculate. Now I said that small u is the same for all particles. Oh, I have some visitors from Austria in my group. They brought this very tasty chocolate. You guys are not going to care for the remaining part of the story because I ate the chocolate. I forgot. But I thought I would give it to someone, but I ate it. So sorry. So how do I simplify this? If U is the same for every pair of interaction, can I simplify this right away and get rid of the summation? How many pairs of interactions do we have in the system? In an n particle system, how many pairs can you have? And choose 2. So what can we write this as? N multiplied by n minus 1 divided by 2 multiplied by average of U of R12, right? On an average, it's going to be the same. Why consider it separately? There are n choose 2 pairs, so just take it out. It really becomes much simpler. This is happening only because U is the same. So this term comes from number of separate pairs we have in this system. Okay, now we can write it down in full mathematical glory. So we have n multiplied by n minus 1 by 2, and we have an ensemble average. How do we take the ensemble average of anything in a canonical ensemble? Yeah, go ahead.
I'm still not sure what the previous. I get the n choose 2 thing.
Yeah.
But I can have, say, one particle here, one here, and the same particle, another particle.
We are talking about on an average. On an average, the interaction between me and you is on an average, the interaction between you and Omar. On an average, the interaction between Omar and Jared. Okay, that's the idea.
So what is R12? It's just
It's just a variable. It's like when you do integral fx dx plus integral fy dy plus integral fz dz, and then you say, wait, f is the same and x, y, and z have the same domain. I will write it down as 3 times integral f of x dx. You could have written it as 3 times integral f of r dr, right? It's just a change of variable. So any 2 particles, okay? So this happens only because the small u's are similar. So now we have this, and now we have to compute an ensemble average in the canonical ensemble. Now you're all masters of that. So how do we do that? We will, let's go slowly. So we have in a canonical ensemble, what is the first thing that shows up? Well, the first thing that shows up is the quantity that you're averaging, right? So small u of R12. What should I write here after that? Probability. What's the probability? exp of minus beta. Again, I wish I had not eaten that chocolate. What should be the energy here? Small u or capital U? Why? Not because you have Chandler's book. See, this. Look at him, Patrick. Look at him. If he had Tuckerman's book, would he be sitting there so comfortably with it spread out over his chest? No, he would have suffocated by now. Tuckerman is going to visit here in a month.
Nice doorstop.
Yeah, I've done that with many biochemistry books. You can also use them for dumbbells, things like that. Anyway, let's come back. So it's going to be capital U of Rn. And this thing now is going to be dr capital N. This is not small u. Does that make, is there someone to whom this is not clear? Don't be shy. He's never shy. Oh my God. Why is this not clear to you? Tell me. What do you think? It should be small u?
no. It should be the total energy.
It should be total energy because I'm thinking about the interaction between 2 particles, but I have to average over what everything else is doing. That's the problem. Okay, that's how we did probability distribution, right? That was the thing with, this is why this stuff is so hard. You cannot just look at 2 things. Anytime you're talking about the energy between 2 things, you have to average over everything else, right? Otherwise, it would just become the potential energy and we would be done. Nothing remains. The problem is, it is the potential energy averaged over what everything else in the environment is doing. That's what makes the math complicated. What will we have in the denominator? Everything except small u of R12, right? So this will be exp minus beta capital U of Rn multiplied by drn. Okay, now let's do some algebra here. Let's keep the half out So this half that I have over here, I am keeping it out. The denominator, I am going to do nothing. The denominator, I am going to just write down exactly how it is. The numerator, I'm going to split this one. So what is the meaning of dr capital N? That is dr1, dr2, dr3, dr4, right? So I'm going to write down dr1 and dr2 in the very beginning. And this n minus 1 that I had, I'm going to bring it over here. It will become clear in a moment why I'm doing all this. So n multiplied by n minus 1 comes over here. What am I left with? I'm left with dRn minus 2, right? Because R1 and R2 have been accounted for. So Rn minus 2 multiplied by exp of minus beta u okay. Did I miss something? I missed something, right? I missed the u, small u. So I should have written here small u R12 multiplied by n minus 1. We are almost out of your misery. Just one line and we are done.
Will it still be Rn for the exponent e power? Because you're considering the n minus 1.
Yeah, but I don't know how to remove that. That capital U is some complicated function. It depends on everything, right? Yeah, it's not separable. It remains there. Now, some magic will happen. And all of this will suddenly become very beautiful. This thing in the green bracket, in the green circle. Have you seen this before? Huh?
Yes.
Yes, good answer. What is it?
This is that gradient force.
It's simpler. Think about, let's make it even simpler. Think about, I hope it becomes even simpler. Think about this part in the orange. What is this part? I remove the n minus 1. Ignore everything. Ignore the n minus 1 and consider only the part inside orange. What is that? Yeah, and if you multiply it by n minus 1, what is that? That is rho 2. So let me write it down. So basically what we are saying here, so let's call this equation 3. So recall, and this is why you might forget the steps of this derivation. I really hope you do not forget equation 2. That's important. The steps are complicated, but equation 2 has an intuitive reason for it. So hopefully you will remember that. So rho 2 of R1, R2, how did we get that from P2 of R1, R2? It's n multiplied by n minus 1 multiplied by P2 of R1. Is Kinjal still with us or have we lost him?
No, he fell yesterday.
He was
Yeah, it was up late.
homework 3 and 4 took a
Toll on him. Like I got his Slack message like 4:30 a.m. or something.
Yeah, he had a lot of students last night.
Students?
Yeah, and he's like in the class.
Okay. So we have this, and what is P2 of R1, R2? P2 of R1, R2 is exactly what we have in the integral. You go and integrate out everything else that you have except R1 and R2. And in the denominator, you have the full partition function. So that's equation 4. So equation 4 is telling us that all of the stuff that you have in the green bracket is simply rho 2 of R1, R2. So what are we left with? We are left with capital U of Rn is equal to half integral dr1 integral dr2 small u of R12 multiplied by rho 2 of R1 comma R2, which is what we wanted to prove, right? And again, if you're getting lost, first of all, you should not get lost in the algebra. If the step that we took to get to equation 4 is confusing you, that's a sign that you should not be confused at this point. Okay, you should think what's it going on. So, but you might not be able to derive it on your own if I just gave you a piece of paper. But if I gave you a piece of paper and ask you to write down the average energy for an n-body system made up of only pair interactions, you should be able to write down this equation, okay? Because it makes intuitive sense. Okay, let's try to do that together. I don't have my notes, I removed it. So what do we have for our average energy E? That's going to be kinetic energy average plus potential energy average, right? What is kinetic energy average? That is 3/2 NKBT. What is potential energy average? We have to go to every particle for R1, every particle for R2. We have to multiply by the energy that it would have if it was at 1 and 2. What are we missing here? The probability of finding those particles there, but it can be any two particles. So it will be rho 2 of R1 comma R2. But now we have double counted, right? So we have to divide by half. So you can see this equation is not hard to remember. Okay, so remember this equation and we will use this. If the proof confuses, that's okay. Any questions? So we are still dangling R1 and R2. Let's simplify it one step further. So this was equation 2. Now let's think about when we dealt with this P2 and rho 2 and all this business, we said, well, most of the times we are just going to care about spherically symmetric molecules, just only radial distances, right? And it kind of makes sense. We are talking about a system with only pair interaction and radial distances. So why should we worry so much? So here's a question. If a system has only pair interactions, does this mean that the system will always be arranged in a radially, in a spherically symmetric manner? If the interaction between all the particles of a system are only radial, they only depend on the distance, does this mean that we really need to worry only about G of R and we don't need to worry about things like G2 of R1 comma R2? We don't need to worry about angles. Huh? Why? Let's not go to Henderson theorem, but I can give you an example. So if things were point-like particles, then it won't matter. I think it will come out to be simpler. The problem happens when these particles have dimensions. Okay, so, and I'm going on a tangent here. I will mark tangent so no one gets confused. But you can go and read up. Onsagar had done a lot of work on this. It's known as the nematic transition. So imagine you have particles that are like this, and they have only pair-like interaction. Everything is fine, right? It will be only radial. There will be no symmetry coming due to angles and things like that. Now let's imagine these things are slightly bigger. It's still going to be probably the same, right? They're just moving around. Now let's do something. So we started with point-like particles. And from that, we gave it some size. This is not going to be the exam. So it will probably not be on the exam. So now let's make these things slightly asymmetric. They are still point-like interactions, but the particles themselves are rods. Now everything changes, right? So Onsagar was the first person to study things like this. He really started thinking about what if the rods are very, very long? And then you can come up with very complicated phases, even in a system with pair interaction, hard sphere-like pair interactions. If the particles have certain geometry, the picture can completely change. So, and then, yeah. yeah, let's come back from this. Let's come back to what happens to equation 2. What happens to equation 2 if we had spherically symmetric molecules? What should we do to equation 2? What's the first thing we should do? We can simplify rho 2 of R1, R2, right? So we can write down rho 2 of R1, R2 for spherically symmetric molecules. Anyone remembers what's the expression for this? Arman, do you remember? In G of R, in terms of G of R? Here's your hint. If the system was completely independent, nothing talks to anything, then what is the value of rho 2 of R1, R2? It is square of the density, right? So that's how you remember this. It's okay if this does not come to your mind right off the book, because it's the first time you all have seen this. But this is going to be true only for ideal systems, right? Where there's no interaction. What correction did we introduce here? G of R, right? So for spherical system with interactions, rho 2 of R1, R2 is equal to rho square G of R, right? By the way, when I ask any of your questions in the middle of the class, it's not to prove anything, right? First of all, I think it helps people stay alert. And secondly, these are complicated concepts. You know, you have not thought about things like this previously. It takes time to become comfortable with things like this. And to be honest, you guys do the same to me. You ask me questions all the time, so it's got to be symmetric. So we are going to use this. And for this, we can write down the average potential energy, the n body. Let me go to the next page. So if we have rho 2 of R1, R2 is equal to rho square G of R for spherically symmetric molecules. And reminder that rho 1 of R1 was rho also for spherically symmetric molecules even with interactions, right? So we did not talk about something like G of R for one particle case, right? G of R was essentially a 2-particle construct. You need to have 2 particles, right? So this is true for anything with interactions, because G of R is what accounts for those interactions, right? So let's call this let's call this equation 5, and let's call this equation 6. So the thing that we derived for U is equation 5. I also called it equation 2, but that's okay. So let's use 6 in 2. Let's use 6 in 2, because I'm not going to worry about the kinetic energy part. So what do I get? I get capital U of Rn is equal to half integral. And now I will be careful to write the vectors, because what we really mean are vectors going on here. While this small u is not a vector, right? The small u depends on the distance. So R12 is actually modulus of the vector, right? Multiplied by rho 2. And this is also these R1 and R2 are also vectors. Okay, so let's write this down explicitly and using equation 6. So this is going to be half integral d R1 multiplied by integral d. So I will come back to this dr in just a moment. Here I'm going to write it as u of R12 multiplied by rho square g of R12, right? G depends only on the distance. So this dr2 that I had can actually be replaced by dr small 12. Does that make sense? So I had 2-dimensional integration over 2 vectors, but what really I'm doing is to fix the vector for the first coordinate And then the second thing is only the distance from that, right? So the first integral is a vector and the second one is just a distance. Huh?
Are we missing the solid angle?
No, I don't think so. I don't think so. I don't think we are missing solid angle. No. I will make a note here. I don't think we are, but yeah, I will make a note so I can look at it. Are we missing solid angle? I don't think we are.
The way I see it is,
Yeah, I see why you're saying it, but I don't think we are because that's accounted for in R1. It's really coming due to the structure of row 2. But let's get back to this. Okay, for now, let's stay with this. So once we have this, this R12 is just a variable, right? It's like we did earlier when we got deeply disappointed. We can call it by some other name, right? We can call it D Vedant. It doesn't matter, right? We won't do that. We will call it D small r. Okay, so we will just call it D small r, U of r, rho square, G of r. So now turns out that this integral and this integral are just products of each other. There is no R12 in the first one. And what is integral of dr1? It's the volume. So this becomes half volume, rho square comes out, rho square, integral dr, u of r, g of r, right? So we have just shown that for a system made up of only spherically symmetric particles, capital average value of the total energy is equal to 3/2 nkbt plus half v rho square is equal to v rho multiplied by rho, right? What is v rho? V rho is n, so it is n multiplied by rho, right? So half n rho yeah, you're right. But that's simple, right? All we need to do for solid angle is to put a 4 pi r square, right? Yeah, 4 pi r12 square. That's it. So 4 pi r square, that dangles. So 1/2 n rho dr 4 pi r square g of r u of r. I just remembered because in your homework 5 that now all of you are going to try, there is a term you are going to prove what this, something very similar to this is there, this integral. N is dangling everywhere, so we could remove it to the left side. Yeah, go ahead, Sophia.
How do you go from the dr1 vector to r?
Oh, I just gave it a name. I could call all of this as dr12, 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 r12. It's kind of long, right? So I just renamed. I called r12 as r.
But the one in front of that, the dr.
The one below or above?
The dr1 vector, that's on the side, the left side.
This one?
Yeah, and then below it, you have it circled in black.
Oh, so okay. Let me write it down a bit more clearly. So the point here is that this thing does not, this blue circle does not depend on R1, right? It depends on only R12. R12 is the distance from here to here. R1 is the distance from here to here, right? So it does not, this is R12, this is R1. So it does not depend on that. So the integral in red, and the integral in blue are completely separate. And the integral in red is just volume. Integral of dr1 is just volume. So this thing becomes half multiplied by volume. That's this integral. And this one becomes dr 4 pi r square rho g of r u of r. Okay. So we bring the rho outside, rho square, sorry. So we bring the rho square outside. So this becomes half rho square v integral dr 4 pi r square g of r u of r. Okay. So we have just shown that the average total energy is equal to 3/2 n kBT plus half rho square v can be written as n multiplied by rho, right? Because rho v is n rho dr 4 pi r square g of r u of r. So if you are interested in the average energy per particle, the intensive quantity, that's going to be 3/2 kBT equipartition, right, per 3 degrees of freedom, plus half multiplied by rho multiplied by integral of dr 4 pi r square g of r u of r. So this is the equivalent result for spherically symmetric. This not equivalent, this is the result for spherically symmetric particles in presence of interaction. So why is this equation useful? You will see the use for this when we do statistical mechanics perturbation theory. But otherwise, also you can see why it's useful is because, let's say you are a computational, you are running a chemistry lab, and you can measure G of R using some scattering experiments, right? And you really don't like to do molecular dynamics simulations because they're very expensive. All you can do is density functional theory, zero temperature density functional theory. That will give you U of R, right? That's what DFT does. You can figure out the U of R, the interaction with U of R is not temperature dependent, right? U of R can be calculated from zero temperature calculation. So there are ways to calculate U of R. If you can calculate U of R, furthermore, U of R does not depend on the presence of other things, right? U of R is just how two things talk to each other. U of R is kind of magical. So people do density functional theory calculations where they very accurately calculate U of R for two iron atoms. It's actually really complicated because iron has not just S electrons, it has P and all these funky electrons, right? So the U of R versus R for iron looks like this curve, but with very, very complicated peaks and local minima and maxima in the middle, depending on what the electrons are doing. But you can measure it. You can measure it using quantum mechanics by using software like Gaussian, things like that. So if you have U of R from quantum mechanics, and if you have G of R from experiments, now you can talk about average energy at any finite temperature, right? And that's kind of powerful that you can do something like this. So this is one way why G of R is useful. I posted an article online known as Henderson's theorem, which is very interesting. The first time I read about it, I was like, wow, this is life-changing. Today is the day I read about Henderson's theorem. It's so powerful. And then when I told my colleague John Weeks about it, so John Weeks was like a PhD student when Henderson's theorem came out. And I think it hit on some like raw nerve or something. Maybe Henderson was a reviewer for his paper or something. He goes, this is crap. It's terrible. Oh, no one cares about it. He just went like ballistic for 5 minutes. But Henderson's theorem is very interesting. Henderson's theorem says, and I posted a one-page proof on this online that you can read. Henderson's theorem says that for a system with only pair interactions, which is never going to be true, but if you're assuming only pair interactions, G of R uniquely determines U of R, which is profound, right? So it says that if you have measured the G of R, you must have the same U of R. You cannot have two different pair interactions giving you the same G of R. It's not going to be possible. So read that proof. It's on Slack. Proof is on Slack. You can read it. I'm not going to ask you about it, but it's something that you should know of. It's kind of useless because it does not tell you how to find U of R from G of R. It does not give you a recipe for that, right? So it's like a mathematician's proof that given G of R, there exists a unique U of R. It does not tell you what it is, right? So, but it's still powerful that something like this exists. Any questions about this? No questions? Okay. So, yeah, so read up the proof of Henderson's theorem. It uses, it's an interesting proof because it uses something known as a KL divergence, which is a distance which is known to be positive. It's a nice one-page proof, but it's useless. It does not tell you how to go from G of R to U of R, but it tells you that if you have measured the G of R, you can, in principle, do some inverse problem and figure out U of R. But yeah, I'll leave it at that. So it's not exactly useful, but it's interesting. Okay. So what did I do so far today? I just derived the relation for how does the average potential energy of a system change with the presence of interactions, right? So what I want to do next, and I'm not switching gears, it's the same thing. I'm really going to talk about interacting systems only, but it sounds like a whole majestic name, but it's actually kind of simple and the relation is very beautiful. I'm going to talk about statistical mechanics, perturbation theory. So the equations that I'm going to derive next were first bold. Were first derived by Zwanzig in 1954, when I think he was a PhD student. So back then, people used to write a lot of single author papers. So he was a PhD student at Caltech with Kirkwood, and it's just a single author paper. You know, back then, publish and perish was maybe not there. You know, so you could still stay in science even if you didn't have too many papers.
Was his rotation problem?
It was that I don't know. A year later, sorry. So Zwanzig came up, and I will post this paper online. You can read the original paper. So Zwanzig wrote this paper in 1954. I think it was either Journal of Chemical Physics or maybe Physical Review. Back then, it was just one physical review. It was not A, B, C, D, E, F, X, L, whatever. However, it's very interesting that Feynman had effectively the same idea, which he also published either in 1954 or 1955. Zwanzig's papers are 5 parts. It's paper A, paper B, paper C, paper D, paper E. Feynman's paper was a one paper, and which was related to something known as polarons. And these 2 papers came out basically in very, very quick succession, which had the same idea in how to derive properties of interacting systems by thinking about them as a perturbation over non-interacting systems. So this existed for a very, very long time. Then in late 1990s, similar ideas were really used in this method known as free energy perturbation, which is a way to calculate properties such as binding free energies of molecules against proteins or RNA or DNA by using equations like this. Its short form is FEP, and this became very, very popular. There is a company known as Schrodinger, which basically made a ton of money out of this. They are a publicly traded NASDAQ company. And one of their best-selling products is free energy perturbation, which almost every pharma company uses before they actually go and make drugs in the lab to screen how something will bind. It's also goes with the name of a very fancy name of computational alchemy. So alchemy is what chemistry used to be known back in the day, right? You could change everything into gold. So here you can change anything into anything else. The same thing has become even more relevant in machine learning, specifically in deep learning, where people realize that when you're trying to train a very, very complicated machine learning loss function, you're trying to minimize a loss function, you can think about the loss function as coming from a simpler machine learning model, and then the loss function is actually convex, and you can do all sorts of funky business. And the machine learning people, they reinvent things. They ignore StatMech. They definitely ignore chemistry. And they called it variational inference. And that's all basically just these two papers by Zwanzig and Feynman in 1954. So I really, really like these papers. So I will tell you what these equations look like and why they are so powerful. And I will tell you, I will use them in theory over here and how to use this to get van der Waals equations. Now I am really going outside Chandler. Chandler does not cover this. This topic is in Macquarie's book. You can find a PDF online if you look hard enough, or maybe not even too hard. Macquarie chapter 14 does this, okay? So let's see what this means. So the idea is that if I have a complicated n-body potential, okay? And I'm going to use a shortcut for it. I'm going to write it as U subscript capital N, okay? Everyone stay with me on this, okay? So U subscript capital N is just indicating complicated n-body potential, where everything talks to everything else. Let's think about this as coming from some reference n-body potential. So we call it superscript 0, okay? Plus a perturbation on that reference potential, okay? Which we call superscript 1. Perturbation, and this is reference. So what could this look like? For example, you have two particles that are interacting through some spring, right? And you could think that this is coming from a reference with no interaction plus the spring being a perturbation, okay? Right? In this case, it's trivial. In this case, UN of 0 is 0, right? There is no interaction. So this is trivial, but hopefully it conveys the picture to you, what I'm trying to go after. So with this, I'm going to do a bit more algebra, which is going to look like the algebra that we have been doing, right? Writing down complicated integrals and saying, oh, this is just an ensemble average. But the equation that comes out is really beautiful. So let's call this as, this was equation 6. This is equation 7. So I want to think about the canonical partition function. And this is the true potential, okay? So we have 3 terms here, true, reference, and perturbation, okay? So let me write down the canonical partition function for the true potential. That's going to look like Z, and I will call it subscript N to show that it is the true one and nothing in the superscript, okay? Anytime it's a reference, I will write down superscript 0. So Nick, what will this be? Canonical ensemble, partition function. E to the power something.
Yeah, is it e to the power of negative beta?
Uh-huh. Which U should I use from equation 7? You have 3 options. It's for the true system. That's your hint.
So yeah, so the
True UN.
UN.
Yeah. I mean, I ask very simple questions. It's not profound. So this will be UN, right? Okay, I woke Nick up. We should have wake up. Vedant is definitely awake. Vanessa. What should I integrate over here? D of Rn being? Should I integrate over every particle? It's the n-body system. That's your hint. So we talked about two types of Rn, right? Are you referring to this Rn? Yeah, then it's correct. So, but what is that Rn? That Rn is dr1, dr2, dr3, dr. So when I write R superscript n, remember that is actually a shortcut for the complicated vector, right? Of R1, R2, R3, right? So this is the true canonical partition function for the true potential, e to the power minus beta un something multiplied by all the particles. So now let's use equation 7 in this. Okay, and pay attention. It's going to look like magic. What's going to happen next? So I'm going to write this as e to the power minus beta. What is un? Un can be written as un0 plus un1, right? So let's do that. Let's write it as un0 and e to the power minus beta un1, dr1, dr2, drn. And just like Vanessa said, this a shortcut for this is dr capital N, which we had been using, right? So, but I want to write it down explicitly. Okay, we have this. Now I'm going to do another magic. I'm going to multiply and divide by the same thing. Okay, I'm going to multiply, divide by integral of e to the power minus beta un0 dr1, dr2, drn, and the same thing in the numerator, e to the power minus beta un0 dr1, dr2, drn. Does this thing have a physical significance? It's the partition function for the reference system, right? Is that clear, Nick? When you asked me to put u capital N subscript true, that was the reference function for, that was the partition function for the true system. If instead of that, if I replace this with this one, then it will become partition function for the reference system. So I have just multiplied, divided by the partition function for the reference system. Okay, so stay with me, and this equation is important. I'm going to write this down on next page once again, because we are going to manipulate this. So we just, what are we writing down? So we wrote down Zn. Zn was integral e to the power minus beta u true system. Okay, so no superscript. It's the true system multiplied by d r1, dr2, drn. And we multiplied, divided it with, no, at this point we said that let's think about this as e to the power minus beta un0 e to the power minus beta un1. So the reference potential plus the perturbation. Okay, both are there. dr1, dr2, drn, and then multiply, divide by e to the power minus beta un0 dr1, drn, e to the power minus beta un0 dr1, drn. Okay, and this thing is Zn in the reference potential, right? This thing was Zn and this thing is Zn0. This thing is also Zn0, right? I have just multiplied, divided by the same thing. What I'm going to do next is to keep this one. The one in the bottom, I'm going to keep the full integral. The one on top, I'm going to call it Zn0, and you will see why it makes sense in a moment. So this one comes up front. I call it Zn0, and then I write down this integral over here. That becomes e to the power minus beta un0 e to the power minus beta un1 dr1 dr2 drn, and in the bottom we have e to the power minus beta un0 dr1 dr2 drn. At this point we can make a magical change. What is that magical change? Go ahead.
It's the average of you
It is the average of e to the power minus beta un1 in the reference potential, in the reference ensemble, right? So the magic is, I mean, at that point, if I was a reviewer, I would have almost been tempted to say what you derive is trivial and be very jealous, like he thought of it and I did not think of it, right? It's almost at that level. It's so simple. So just to give you a sense that if I had e to the power minus beta un0 multiplied by some function that depends on r1, r2, rn, multiplied by dr1, dr2 going till rn, divided by e to the power minus beta un0 multiplied by dr1, dr2, drn, then this thing is nothing but the canonical ensemble average of f of r1, r2, rn. But we have to be careful that this average has been calculated in the reference potential, right? The potential energy that you used over here corresponds to the reference potential energy. So now what have we done? Our f happens to be e to the power minus beta un1, which is a function of r1, r2, r3. So what we are saying here is that Zn is equal to Zn0 multiplied by the average value of e to the power minus beta un1 in the reference potential.
What does that mean? This is when you're calculating the average as well.
Yeah, so it means that, let's say, since you asked, let's say Vedant and I are connected with a harmonic spring, right? Anytime we get too close, he pushes me away. Anytime we get too far, he's like, where are you, Professor Tiwari, come back. That's a harmonic spring, that's what it does. And we want to calculate some average property for Vedant Pratyush interacting system. But what we can do instead is to simulate Vedant and Pratyush as ideal particles, or study them as ideal particles, which is going to be very easy, right? Doing the math, because we are ideal particles. But at any point, we will calculate the value of the potential energy and take its exponential and just average it. So you don't have to do the dynamics in the reference potential, in the true potential. You have to simulate, you have to study a reference system to get and to see what value would you have. It will become clear as we go to further examples, but let me write it down on the next page and I will give you more intuition. So the equation just we derived, which is the main relation for stat mech perturbation theory, is that the partition function for an n-body interacting system can be calculated from the partition function for a reference system. It could be non-interacting, it could be some simpler system, by simply calculating the average value of e to the power minus beta multiplied by the perturbation that you added to the system in the reference ensemble. So what does it mean in principle? In practice, let me give you an example. So let's say our U of n is ideal gas plus Hooke's law, okay? Harmonic springs. So ideal gas plus half kr square type interaction, okay? And I'm being sloppy here because I'm trying to give you intuition. So don't grill me on the math. So ideal gas, which is 0 plus half kr square. So in order to calculate this, I will simulate an ideal gas or study an ideal gas or do the math for an ideal gas. And I will calculate the average of e to the power minus half beta kr square in that ideal gas. What does this look like? It means that in an ideal gas, this configuration is equally likely as compared to this configuration, right? All of them are equally likely. can be here, you can be here, you can be as far as possible. But for each of them, you can calculate what is the value of R, right? This will be some value of R, which is large. This is some smaller value of R. This is some even tinier value of R. This is some even tinier value, larger value of R. For each of them, you calculate R. R gives you e to the power minus half beta kr square, and then you just take a sum of it in the reference potential. Okay, so you see why this is important, because harmonic springs can describe so many interactions, for example, right? But here you are talking about the properties of a harmonic spring by instead simulating argon or krypton, where there is no interaction.
But wouldn't you require that perturbation that you have is very, very small?
Yeah, that's the point I was getting for. Why? This, okay, important point. This equation is exact. This equation does not say the perturbation has to be small. So why do I want the perturbation to be small? What will go wrong if the perturbation is not small? Why? Why exactly? Where will the convergence issue come from?
You're going to have a hard time sampling reference.
Even simpler, even simpler. So UN is UN0 plus UN1. And for this equation to be useful, the perturbation UN1 should be small. What will go wrong if UN1 is large?
Oh, your exponential.
Exponential of a very small number is going to be a drastically small number. That's why it won't converge, right? If you can think about it, if let's set beta is equal to 1, okay, some inverse temperature. If UN1 is 10, what is e to the power minus 10? Some really small number. If UN1 is 100, e to the power minus 100 is really, really small number. Try doing it in MATLAB. You will just get computer zero errors. It won't work. So Zwanzig's relation is exact, but is useful only if you have small perturbations. So how do people make money of it? Why is it so useful? So the idea is to have gradual perturbations, okay? Don't immediately go from no interaction to full interaction. Turn it on slowly, right? So you go from UN0 to some UN small. So let me write it down a bit more carefully. So what we will do is turn on perturbations gradually. We won't do it in this class, but that's the main idea, why it becomes useful in practice. So how do I explain it to you without getting too much into simulations and things like that? So let me write it on the next page. So actually I can write it down quite rigorously. What you can show that if UN is equal to UN0, we added all the perturbation through UN1, right? But let's do it gradually. Let's add a small perturbation UN1 that is very, very tiny, very small relative to UN0. Now let's add another small perturbation UN2, then yet add another small perturbation UN3. Let's do it over a finite step. Now you can show a relation which will look something like Zn is equal to Zn0 multiplied by e to the power minus beta UN1 calculated in 0. But now UN1 is very small, so you can actually do it, right? Multiplied by e to the power minus beta UN2 calculated in 1, so on and so forth. Why can we do that? Because it's partition function, it's magical, right? It just partitions into. This becomes a practical recipe. This is what people use in free energy perturbation. So, and they do all kinds of crazy stuff. They can change a single bond into a triple bond by turning on the second bond very, very, very slowly. So there are lots and lots of methods for doing things like this. So we won't be doing that. We will be working with only one perturbation. So next time what we are going to do is to take our reference system as hard spheres and then derive van der Waals equation. Huh? In terms of what?
These
No, we will Taylor expand in terms of beta.
Data you want.
Yeah, it will be something like beta. Yeah, go ahead, okay.
So for the second dissipation, are you saying that the first perturbation is the reference?
Yeah. It's you have the right idea, but be careful in your wording. The first perturbed system is the reference, right? So then the second perturbed system is the reference. So for the first calculation, this is the reference. For the second calculation, this is the reference. So on and so forth. So gradually turn it on. So it's alchemy, you're gradually going from one to the other.
So that example, do the subsequent events have to be smaller than the previous one
Everything has to be small related to the sum of the previous one.
to ensure the
Yeah.
entire series?
Yeah. So your homework is out, and I made a point. Please do an honest job at it, okay? Otherwise, I will give you homework 6. There will be a second midterm, which will be out soon. The second, let me tell you a little bit about the second midterm. It will be short. It will have 2 proper problems, okay, that you have to work through, and that will amount to roughly half of the midterm. The other half of the midterm will be you reading a paper and writing a summary of it. So you will have choices of paper. You will have Zonzig's 1954 paper 1. You will have Feynman paper from also the same time. You will have a David Chandler paper on hydrophobicity, things like that. So there will be like 5 or 6 papers, and you can pick any one paper, and I will ask you to do specific things like, what did you like about the paper? What is the main summary? Draw a figure, something like that. So it will be a fun midterm. The 2 problems that I will give will be a bit that they will involve thinking, but the paper itself, we have many papers to pick from. You can pick whichever paper you want. So that will be the midterm. The final will be in class. That's for sure. Alex Freeman has now convinced me to not give him take home mid final.
Delayed a little bit. It ends so early.
Oh, I cannot help it because of the classroom. I'm so sorry. You can come at 9.
I mean, last time I came like 8:30.
I know. This time 9. Do it. Do it. No, I'm really sorry. You think I actually wake up early. Didn't you say you wake up early?
Me?
Yeah.
Sometimes.
So make it that sometime. No, I cannot help it because this classroom will be used from other people, and then I don't know how to find the classroom. So it's a university policy. Sorry. The best part is you will know your grade by 2 p.m. that day. Yeah.
Yeah, but the worst part is like,